Okay, good morning, everybody. So no look now, it's almost the weekend. So how are you guys doing? How was your week? I imagine you had a long one. Yeah, first I finished grading my share of the homework problems. So, but the deadline for all TAs to submit the graded homeworks is tonight at midnight. So you might be able to see your graded homeworks either over the weekend or early next week, depending on when our lead TA can upload it back to CASA. So just take a look at it and let me know if you have some questions on how it was graded. Again, as a disclaimer, I might not be the one who graded your papers because it was distributed among us tutors or among us TAs randomly. So yeah, but if you have some questions on how it was graded or you think you should have gotten more points for a particular problem, then you can let me know. Send me your graded homework together with your question, and then I can take a look at it and make the proper recommendations. Okay. Also, test number 2 would be on I guess next weekend. So I hope you guys started preparing for it. Dr. Almus told us that she already uploaded a practice test in CASA, so take a look at it. I also saw that the answer key was also uploaded there. So one thing you can do is try to answer the problems on your own. If you get stuck at a particular problem, then you can go to the answer key and look at what was the step that you missed so that you can do it on your own again, right? Or if you had really some difficulties on certain problems, you just let me know and then we can probably discuss them in one of our lab meetings next week. But the practice test is quite long, so I don't think we'll have enough time to answer everything. So I hope by next week you can let me know what are some interesting or challenging questions for you guys so that we can focus on them. Does that sound good? Or do you guys hear me at all? So kindly.
Yeah, we hear you.
Okay, great. Thank you. So yeah, do it over the weekend. Start preparing for it. And then for today, I'm thinking let's continue our discussion about centroids. We finished, I guess, one example last time where we set up the integrals that will give us the coordinates of the centroids. And centroids gives us a very useful tool, which is called Pappus's theorem, which is something that tells us how to compute the volume of a solid of revolution, knowing only the area of the plane region that was used to form the solid and the centroid of the plane region. So what I'll do is to complete problem number 36 from worksheet number 4, because if you recall, problems 33 to 38 in this worksheet asks for three things. First, the location of the centroid, and then the volume of the solid form when the region is rotated about the x and the y-axis. So let's complete our solution for problem 36. But before that, a quick recap. What is the centroid of a solid or of a region? Well, it is nothing more but the center of mass. Or if your region has constant density, then you can look at the centroid as the geometric center of a region. So, and how do we compute for the centroid? Well, first you need to find the area because the x and the y coordinates of the centroid are average x and y values, and we average it against the area of the region. That's why if you remember this in this formula, we clearly see that the coordinates x bar and y bar of the centroid has the area in or have the area in the denominator, right? So that's why the area is important. And then the numerator for these coordinates are the weighted integrals of the x and the y variables respectively. And we take the integrals against the length of the strip. So here I used vertical strips in order to characterize the area. So that means to get x bar, I need to integrate something against the length of the strip. That's why I have the f of x minus g of x here. And since I want x bar, I'll take the average x value. So what I'll do is to take all x values, multiply them by the length of the respective strip, integrate from A to B, divide by the area. That's the x coordinate of the centroid, right? Now for the y coordinate of the centroid, again, you still have the area in the denominator. And then the numerator is again an integral, right? And that's an integral against the length of the vertical strip. You still have the f of x minus g of x here. And then we were supposed to take the average of the y values. So this should have been y. But the problem is I cannot put y inside the integral because we are integrating with respect to the variable x. That's why instead of a single y here, I take the average of the y values. Notice that here in the graph, the highest y values occur at f of x. The lowest y values occur at g of x. Since we should remember that the centroid is a geometric center, so we take the middle of that strip. And the middle of that strip is nothing more but the average of the f and the g values. So that's why instead of a y variable here, I will put f of x plus g of x all over 2, representing the average of the y values over the interval. All right. And then if you simplify this, multiply top with the weighting function, you get f squared minus g squared divided by 2, all divided by the area. And that's how we got this formula. Perhaps you have seen this formula from the textbook. All right. That's how we compute the centroid. Now, I guess last time we had this example. We had the region R bounded by the parabola x squared plus 3x, the lines x equals 0, x equals 3, and the x-axis. And we said that the area is 45 over 2. And then we compute the centroid. So we again have the strip. The strips are of length top minus bottom. So that's why I got x squared plus 3x minus 0, right? And that goes inside the integral for both the x and the y components, all right? And then the area goes in both denominator, okay? And then for x bar, we integrate against the variable x, which is perfectly fine because we are integrating with respect to x. So we got this, and I guess I left the evaluation of the value to you guys. But if you do the calculations, if I'm not mistaken, it's 21 over 10. And then for y bar, you still have the length of the vertical strip over here times supposedly y, but we cannot put y inside of that. So instead we take the average y value. The top y values are from x squared plus 3x. The bottom y values are from y equals 0. You take the average, so you get the sum, divide them by 2. So you get that in the integral. And then some manipulations will give us this. Okay. And when you evaluate, you should get 279 over 25. Let me just double check this. Okay. If this is the correct value. So I'll have x squared plus 3x quantity squared minus 0. Integrate from 0 to 3. So this would be 2511 over 10. And then I multiply by 1 over 45. So yeah, I guess this is 279 over 50. Okay, guys. Let me see, because I had some doubts about it earlier. Is it 279 over 25 or over 50? It's over 50. So yeah. Or did somebody try to evaluate this? Or you also hate evaluation? So that's 2 over 45. That's 1 over 45 times that integral. So 279 over 50. Okay. So that means if you go back to our region, Remember, our region looks like this. It goes from 0 to 3, right? So x bar is 21 over 10. So that means that's about over here. And then 279 over 50. What was our y value here? Let me just go back to the graph. It was 18. Okay. And it's 279 over 50, so that should be somewhere here. 279 over 50. So that means this point over here is the centroid, which is the geometric center of the region. And one thing is for sure, the centroid should be inside the region, right? Because that's the geometric center of the region, so it makes sense that it should be inside. If you do the calculations and it happened that the value that you computed is outside of the shaded region, then you had the wrong centroid. All right. So I hope that's good. Now let's move on to parts B and C of the problem. So maybe I'll just make a conclusion here. Therefore, the centroid is at 21 over 10 and 279 over 50. These are the coordinates of the centroid, okay? All right, part B of the question asks us to find the volume when R is revolved about the x-axis. Okay, so if the problem didn't tell us to use any particular method, then it's up to you. It doesn't matter what type of technique you use to find the volume when the region R is revolved around the x-axis. So the axis of revolution is over here. You can use the cylindrical shells method, or you can use the disk method in order to find the volume. But for this problem, we were specifically told to use Pappus's theorem, and I guess that's more convenient, especially if you know the centroid and the area of the region. Pappus's theorem tells us that the volume of the solid of revolution is simply the area of the region times the distance traveled by the centroid. So that's why it is sufficient to know only the area and the coordinates of the centroid of the solid of the region to know the volume of the solid of revolution. No extra integration would be required here. So let's look at this particular problem. So the volume by Pappus's theorem would be the area of the region, but we already knew that the area of the region is 45 over 2. Remember, we computed that last Wednesday because we also used this for the denominator of the coordinates for the centroid times the distance traveled by the centroid. But what you need to know here is that, or to imagine here, is that when you do the revolution of the region, the centroid will travel along a circular path, right? And Pappus's theorem tells us that the area of the solid of revolution, the area of the region must be multiplied by the total distance that was traveled by the centroid. But looking at the figure, and I hope you can imagine that after the revolution, the centroid would have traveled a complete circle. So basically that distance will always be the circumference of this circle that was traveled by the centroid. But what do we see here? Well, again, that circle will have length or circumference 2 pi r. So I'll copy the 2 pi here times the radius of that circle. But the radius of the circle is just what? It's this. But that is the y coordinate of the centroid. So you get a 279 over 50 over here. Yeah, Kevin, you're correct. The distance traveled by the centroid should always be measured perpendicular to the AOR. But don't forget the 2 pi multiplier. because the distance traveled of the centroid will be the circumference of some circle, right? So because again, as the revolution happens, the centroid travels along a circular path. And so the total distance traveled would be the circumference of that circle. And the radius of that circle would be measured from the AOR towards the coordinate of the centroid that is perpendicular to the axis of revolution. Okay. Now let's see if we can simplify this. Cancel the 2, and then I'll have 50 and 45 here. I can cancel their factors 5, so there would be a 9 here, and there would be a 10 here. So that would be 9 times 279 over 10 pi cubic units. That's a multiplication by 279. All right. Oh, this is another thing I noticed with the homework. There are some who use a calculator to finalize the answer and express everything in terms of decimals. So since you are not supposed to use calculators in exam, you can leave your final answers in terms of fractions. And if the numbers are very large, like this one, it's okay to me if you will leave it as 9 times 279 over 10 pi cubic units. That's perfectly fine with me. All right. Okay. Is it making sense? You guys are still with me? Okay. So let's see the next problem. Yeah, when R is revolved around the y-axis. So same region, we know the centroid. The only difference for problem C is that the axis of revolution is the y-axis. Now, but again, we can take advantage of Pappus's theorem. Again, it's area times the distance traveled by the centroid. All right. The area we know was 45 over 2 times the distance traveled by the centroid. But you can imagine that as you do the revolution, the centroid will travel along this circular path, right? And so the distance it travels would be 2 pi times the radius of that circular path. But the radius of that circular path will be from here until there, right? But that is exactly 21 over 10 units. And yeah, Kevin, you're correct. So that's 21 over 10. Then you simplify, 2's will cancel. Here I can take out the 5. Here I'll have that. So I'll have 9 times 21 all over what? All over 2 pi cubic units. Okay, all good? Now, what if the axis of revolution was a y equals say -3? Yeah, this was not included, or axis of revolution like this was not included in the textbook. I'm not sure if you considered such axis of revolution in the lecture either, but it won't hurt if we look at one example, right? So what if the AOR is y equals -3? Well, we can still use Pappus's theorem, and Christina's suggestion is correct. And let's see why she's correct in saying that we will add 3 to the proper coordinate, right? Again, Pappus's theorem tells us that the volume is the area times the distance traveled by the centroid. But as we do the revolution, the centroid will travel along this circular path. So again, we need the circumference of that circle. But what is the radius of that circle? Well, That circle has radius from here until the AOR. And here from the x-axis towards the centroid, we know that's 279 over 50 units. From the y-axis, from the x-axis towards the AOR, that's 3 units. Because remember, our axis of revolution is y equals -3. So the total radius for the circular path traveled by the centroid is 279 over 50 plus 3 units. All right. Okay, is that clear? And that's what I love about drawing pictures, because this will give me an insight on how to properly calculate these things. No, you don't need to subtract the area from the x-axis to the AOR, because that is built into the formula for Pappus's theorem. Because remember, what we are just multiplying by the distance traveled by the centroid is the area of the region. So it doesn't matter if there would be an empty space inside your solid, because the theorem already accounts for that, because this first multiplier is just the area of the region. It doesn't include this hollow portion. All right. So that's the good thing about this formula. It already takes into account those empty space. Then probably last, what if the AOR is, say, y equals 18? And you see, I can have a single region, and we can play around this by simply shifting the AOR from one place to another. So suppose that the AOR is y equals 18. So this is our axis of revolution, right? And again, we want to use Pappus's theorem to find the volume. Otherwise, you will need to use the cylindrical shells or the washer method for this one. But again, take advantage of the fact that we know the area and we know the centroid. Well, but this time the centroid will travel along this path, right? That would be the circular path that will be traveled by the centroid as we do the revolution, right? So it's going to be still the circumference of that circle, so 2 pi times the radius. But what would be the radius of that circular path? Well, we know that that should be the distance from here until there. We need to measure that, right? But from here till here, we know that is 18 units. From here until here, that's 279 over 50 units. So this radius that we'll be looking for would be what? Would be 18 minus 279 over 50. And that would be the volume of the solid of revolution. Okay. Any questions? You are again being quiet, which makes me a bit nervous. Am I making sense? Or do you have any other questions? Or perhaps you already entered the weekend mode? All right. Now, let's try another question, and let me just add it to this worksheet. Say find the volume of the solid that is formed by revolving the region inside. Say let's have x minus 5 squared plus y minus, or y plus 1 squared equals 4. About, say, let's use an x-axis value here, and then let's say x equals 1. All right. So let's see. So find the volume of the solid form by revolving the region inside x minus 5 quantity squared plus y plus 1 quantity squared equals 4 about the axis x equals 1. Well, the problem doesn't tell us what to use or what method to use, so you are free to choose which one, because now we have 3 ways on how to find the volume of solids of revolution. You can do the disk or washer method, you can use the cylindrical shells method, or you can use Pappus's theorem. But I guess for this problem, Pappus's theorem is much easier. Why? Let's see for a moment, but let's examine how the region looks like. If you remember from your pre-calculus classes, this equation represents a circle centered at 5, -1 with radius 2, right? So the center would be at x equals 5. Let's put that here. Y equals -1. Let's put that here. And then the radius is 2 units. So that will bring us to 1. 2 units here will bring us to 3. And then will bring us to 7. And then it will bring us to -3. So imagine this is a circle. I'll be claiming that that is a circle, right? So that's our shaded region. And we want to revolve it around x equals 1. Say x equals 1 is over here. This would be our axis of revolution. Okay. So again, nothing is stopping you from using cylindrical shells or the washer method for finding the volume of the solid. But I'm saying that it would be more convenient to use Pappus's theorem. So here my solution. I'll use Pappus's theorem, which tells us that the volume is the area times the distance traveled by the centroid. Well, what is the area? Well, you can use your usual calculus techniques to find the area, but I'll take advantage of the fact that I know this is a circle of radius 2. And so its area is pi radius squared, which is 4 pi, right? So the area would be 4 pi units times the distance traveled by the centroid, okay? The centroid is a geometric center of your of the region, but we have a circle here, and we know that the geometric center of the circle is the center. So that means that the centroid here is this, the geometric center, which is 5, -1. All right. And then once the revolution of the region happens, the centroid will travel along this circular path. And that circular path will have this radius, right? How long is that? How long is that radius for the circular path? So don't forget you have a 2 pi over here times the radius of the path. Anybody? How long is that path? Or how long is the radius? Exactly, that is 4 units, right? Because here from here until here, that's 5 units, the x coordinate of the centroid. But we don't want to count 0 to 1. That's 1 unit. So net of 4 units length for the radius, right? So that means the volume is what? Is 32 pi squared cubic units. And you see how more convenient it is. This is than using cylindrical shells or the washer method, because you will have nasty integrals for that. because you'll have square roots all over the place. But yeah, you just need to recognize that I have a perfectly symmetrical region here, which is a circle. So the centroid won't require any integration at all. It's just a geometric center, which is the dead center of the circle. And we know how to compute the formula of the compute the area of a circle, knowing only its radius. Okay. All right, and this is one advantage of Pappus's theorem. And come to think of it, Pappus's theorem was probably is attributed to the mathematician Pappus of Alexandria, who lived between 290 and 350 BC, I guess, or 279 to 350 BC. Sorry, AD. But almost 2,000 years later, or 1,700 years later, we are still studying the formula that he invented back then. So you see how strong mathematics, this nice formula, survive all the ages. Another fun story about that is that Pappus's immediate successors didn't know about this formula, and it is just until I think the 1600s that somebody unearthed Pappus's work and translated it into I think into French or some European language. And this work inspired some of the great mathematicians like René Descartes, also Leonardo da Vinci, Isaac Newton, and they used Pappus's theorem for some of their work, or at least Pappus's work inspired them in some of their mathematical discoveries. All right. Okay, any questions so far? You want to answer one more about Pappus's theorem? Yeah, so most of the problems from the worksheet, which is simply things that I lifted from the textbook, are relatively easy and straightforward, except probably for problem 38. So before I go to problem 38, any questions? Any reactions? Or am I the only person in the meeting now? Really, guys, you don't wanna you don't wanna participate? Okay, good. Yeah, good to know that that you're still there. No worries, Kevin. I just want to get your feedback or your reactions. Back in the days of face-to-face classes, I can observe my students' faces and see and guess from there if they understand what I am saying, or at least am I making sense to them. But that's my problem with online classes nowadays. I cannot have a feeling of, or I cannot guess what you're feeling unless you tell me something via the chat. Okay. So let's try problem 38. Or it might just be that the problems are quite easy. So perhaps that's another thing. Okay, problem 38 from the worksheet asks us to do the same three things, find the centroid, and then find the volumes. But this time we have the region R is the triangle with vertices at the points A comma 0, B comma 0, and 0 comma C. Okay, so let's start by looking at the centroid, right? So usually it helps to draw a picture. Okay, so we have three vertices here, one at A comma 0, then the other one is at B comma 0. So here I'm just assuming A, B, and C are all positive, and A is less than B. But this will work anywhere you put A, B, and C. It doesn't matter because the area won't change. the coordinates of the centroid up will just be translated accordingly. But yeah, it doesn't matter where you want to put those coordinates. Okay, as long as you have zeros all over there. So the first line is from A to C. The next one would be from C to B. And the third one will be this. So this is our triangle. Okay. Now, remember for the centroid, we need the area. Well, for this, I need to find the equations of the line, or probably decide first what type of strips to use. Well, I won't use vertical strips here. Why? Because if I will use vertical strips, then if the vertical strip is over here, I will have the blue versus the pink line. But if the vertical strip is over here, I will have the blue versus the red line. So that means I need to split the integral into two pieces, which I don't want to do, right? So instead, I'll use horizontal strips. Because for horizontal strips, the right function is always the blue one. The left function is always the pink one. So no splitting of the integral is required. Okay? But if you want to make your life harder, then go ahead with vertical strips, right? So I'll just choose the more convenient way here. So, but again, we're using vertical strips, so we need to know the equations of these lines. Well, for the blue line, this is the line passing through the points B comma 0 and 0 comma C. And I hope you still remember how to find the equation of a line. So say this is my x1, this is my y1, and this is my x2, this is my y2. It doesn't matter which one you choose to be your x1, y1, and x2, y2. So you'll still get the same equation of the line. But okay, the formula would be y minus y1 equals the slope, which is y2 minus y1 over x2 minus x1 times x minus x1, right? Then I'll plug in the values of x1, y1, x2, and y2. I'll get y minus c equals negative c all over x2 minus x1. So that's going to be b times x minus x1, so over x. And then remember, I want to use horizontal strips. And horizontal strips always go with a variable y. So I need to solve for x in terms of y here. So I'll get x equals negative b over c times y minus c. Or I can rewrite this as b over c times c minus y. All right. Okay, so next, you need to do the same thing to get the equation of the pink line. But I'll leave the solutions to you guys. Kindly verify that if you do the same thing for the lower line or to the left line, you'll get x equals, let's see, you'll get x equals negative a over c or a over c times a minus y. Oh, sorry, you should get c here. Yeah. Yeah, let me just double check. So that would be a positive and then negative a over c. Okay, yeah, I think that's it. Another quick check is to plug in c. I get x equals 0, fine. If I plug in a, I get c minus a. Oh, if I plug in c, if I plug in 0, I get a. Okay, good. So these are our two equations. And remember that the area is the integral with respect to y. And then where is the starting y value? Starting y value is 0, ending y value is c. So we get the integral from 0 to c, and it's going to be right minus left. So it's going to be the blue line, b over c times c minus y, minus the pink line, a over c times c minus y, dy. All right. And then you can simplify this as an integral. You can factor the c minus y out, and you'll have b over c minus a over c. All right. And what will happen here? Well, these are just a bunch of constants. We just don't know the exact values of a, b, and c, but we know for sure they should be constants. So that means I can take it out of the integral sign. Integral from 0 to c of c minus y dy. And then this is b minus a over c times cy minus y squared over 2, evaluated from 0 to c. And then you can continue the algebra, and hopefully you will get c over 2 times b minus a, right? Which actually makes sense because you see that the region is just a triangle. And remember the formula for the area of a triangle? It's 1/2 base times height. Well, we already have the 2 in the denominator that takes care of the 1/2, and then base. If we look at the region, what is the base of the region? The base of the region is b minus a units long. So that's how I got b minus a over there. And then the height would be the length of a perpendicular dropped from the upper vertex. So if you drop that vertex, the length of that perpendicular line is c, and hence you get c there. Yeah, those A, B, and C, those highlighted, I guess Bao is referring to this. Well, A, B, and C are constants. They are numbers. We were not supposed to compute for A, B, and C. We were told to find the centroid and the volumes of the solids formed by rotating the region with respect to some axis of revolution, but we were not told to find A, B, and C. As such, I'm not looking for them, so I will treat them as constants. Okay. Another way of looking at it is that, remember in this integral, the differential tells us what is the variable that we are integrating with respect to. So here the differential is y. So that means we are integrating with respect to y. All other letters that you see are to be treated as constants. All right. So that's why b over c minus a over c doesn't involve the variable y, so this should be treated as a constant. And as such, a constant value or something that is treated as a constant can come out of the integral symbol, right? And then here I still have a c trapped inside the integral, but the integral of a constant is just a constant times the variable. And then y is the variable of integration, so we have y squared over 2. And Kevin, I don't think we'll have enough information to solve for the values of A, B, and C, but luckily what we are supposed to find here is just the centroid and the volumes. And since we don't have enough information for A, B, and C, our answers for the centroid and the volumes will all be in terms of the constants A, B, and C. Okay? So now we get the area. And remember, the area is useful for the centroid. By the way, I hope that answers your questions, Bao and Kevin. Let me know if you have further questions on that. But let's move on to finding the centroid. So the centroid has coordinate x bar. equals area in the bottom, okay? And then integral, we integrate it against the length of a vertical strip. Sorry, not vertical, but horizontal strips in this case. So we are integrating against this guy. So you can copy this over your setup for the centroid because this is the length of the horizontal strip. Then here, what are we supposed to integrate? We want to integrate the x values with respect to that weight because we're looking for x bar. So we want to get the average of all x's. So what I was supposed to do is to put an x here because I'm looking for the x coordinates. So I will look for the average x value, but I cannot put x here inside the integral because I'm integrating with respect to y. So instead of the variable x, we will just put the average x values. Right? So this should not be there. If you look at the figure again, the average x value will be the middle of the strip, and that will be just the average of the x value on the blue line and the x value on the pink line. And to find the average, we simply add those things up. So let me just put this up here, paste something here. I'll add them up instead of subtracting, because remember, this is from the blue line. This is from the pink line. I want to get the middle, so I sum them up, divide by 2, and you get that. Yeah, such a long equation. I think it would have been better if we have specific values for A, B, and C, then that would be straightforward, right? But I hope the setup makes sense, because from experience in exams, usually you just need to evaluate a couple of integrals, but for most of the problems, you only need to set up the integral for the volume, for the centroid, for surface area, for arc length, and so on. So I want you to focus here on the setup. I hope the setup is making sense, be it you are following the way I'm solving the problem or you are memorizing the formulas from the lecture. All right. But again, in this long integral, A, B, and C should be treated as constants. We are integrating with respect to y. Okay. And if you do the long calculation, you get 2/3 of A plus B. That long equation just simplifies to this nice expression. That means that will just be 2/3 of A plus B. Then similarly for y bar, again, we take the centroid. It will have the area in the denominator. We integrate over the bounds for y. We weight it against the length of the horizontal strip. So you still have that factor there. And then we are looking for the average y value. So I will integrate all the y's against the length of the horizontal strips. And can I keep the y here? Fortunately, yes, because we are integrating with respect to y. So this looks much simpler than the integral for x bar. But if you simplify all these things, you should get C over 3. That nice expression over there, if I did the calculations correctly earlier. So in summary, here, the centroid is at 2/3 of A plus B, comma C over 3. These are the coordinates of the centroid. And then let's answer part B. Part B is asking us to find the volume. Let me just copy the region here. Because I always love to analyze the certain problem with a visual aid. Okay. So for part B, we need the volume when the solid is revolved around the x-axis. So our axis of revolution is over here. Okay. Now I'll take advantage of Pappus's theorem and our knowledge of the centroid. The centroid is said to be at 2/3 of a plus b, so that should be somewhere here. And it's c over 3. So the geometric center is somewhere here. Let me move it a little bit. Okay, yeah. So, okay, so this is our region. We know the coordinates of the centroid. Of course, my figure was drawn not to scale, so it doesn't appear to be really the centroid being in the geometric center, but believe me, it should be there if you draw the figure to scale. And then again, the volume will just be area times the distance traveled by the centroid. The area of the region we knew to be c over 2 times b minus a, right? And then the centroid will travel along this circular path. So here we go. And this circular path will have this as radius. So that means here the distance traveled by the centroid is 2 pi times the radius of that circular path. But that circular path from here until here, the radius of that circular path will be from here until here. But we knew that would be c over 3 units long. Right? So that means that the volume would be what? It would be c squared times b minus a all over 3 pi units or cubic units. Okay. All right. Let's go to part C. Okay. Thanks, Kevin, for the feedback. Same reason here, similar question, but the only thing that changed was the axis of revolution. It was put at the y-axis. Oops. And we knew the centroid would be here, somewhere over there. Okay. Okay, so the volume is still area times the distance traveled by the centroid. The area is c over 2 times b minus a times the distance traveled by the centroid. But as you perform the revolution, the centroid will travel along this circular path. Okay, and so the length of that path will be the circumference of the circle with formula 2 pi radius. But the radius of that circle from here until here would be the x-coordinate of the centroid, which is 2/3 of a plus b, right? That would be times 2/3 of a plus b. So this would be what? This would be cancel the 2's. So you will have 2/3 c times, I guess you'll have b squared minus a squared cubic units. All right. So yeah, that would be some cool applications of the centroid. Oh, it's already 3 minutes beyond time. I apologize for taking 3 minutes too long for today, but I hope this helps, at least for your understanding of the centroid. So for next meeting, we'll do some discussion about exponential growth and decay plus improper integrals. And again, if you have some questions about the practice test or for your preparation for test number 2, let me know on Monday so that we can discuss them, all right? Okay, so you guys have a good weekend, and let's see each other again on Monday. Bye, everybody.